Now, up to this point, we sort of have something about the evolution of the forward rate, but we haven't really got the BGM model because we still have this drift here, which is actually not the drift of the full expressed in terms of the volatility of the zero coupon bond price volatilities. So we have to, change, we have to express this in a different way because right now it's not really the process that's for the forward rate because we're still using the information from the zero coupon bond price, which is something which is related, but so this process itself is not a standalone process. So let's see how we can get that. Now recall that we actually have a relation here. So the ratio between two zero coupon bonds between say T to TI and T to TI plus one, just two different time points, the maturity is equal to 1 plus this delta, which is the time difference, times this forward rate. So forward rate is annualized. This delta just make it in cases like a quarterly or something, 3 months. Then you have to multiply by 0.25. Now, so the forward rate is related to the price ratio of zero coupon bonds in this way. And then you can just take the log, then the log of the difference, the log difference, the difference of the log of two zero coupon bond prices is equal to the log of 1 plus delta IFI. So you then have this expression. Now here we call this a function of Fi. It's a function of forward rate. So because it's a function, then by Ito's lemma, this function has a process. This process will have some drift term and plus some volatility term here. Now, we don't have to worry about this. What we are really interested is this volatility term here. Okay, so this part must be evolving according to this. Now, what is this partial derivative, dg and dfi? Well, if you take the derivative here, from here, you have this 1 over 1 plus delta IFI, okay? Now, multiply this with that, you will have this thing here, right? So basically this red one here is this. So what is it equal to? It's actually equal to the difference of the volatility volatility function for two different zero coupon bond process. Why? Because if you look at it here, if you look at the difference of the log prices, that process will have some drift turn and plus a term that is the difference between the two volatility parameters or the two volatility functions, one for each of this process. So this VI is the for price dPTTI. And this VI plus 1T is the volatility for dP. So dP will be RP dt plus VI plus 1T P T TI plus 1 dz. Okay, so you have this. So basically, this part is just this. So then you can substitute this into this thing that we have seen earlier. So here we required we still are using the volatility parameter for zero coupon bonds, but we now know how to substitute this we need to substitute by here. So now we have got our BGM process, or the LIBOR market model process, which is something like this. Okay. So why do we have a summation here? Well, the summation is because when we have this thing here, this difference is actually a sum. To see why this is a sum, let's say take an example, if k is equal to 5 and m is equal to 1. So for so between the 1 and 2, so there's a drift change here. So k, so if m is equal to 1, then we have, first of all, from 1, which is m, so you have to have a k2 there, k is equal to 2 there, and then there's another point is k equal to 3, and the volatility for that one, the drift for that one is really, 1 to 2 and 2 to 3. And if k is equal to 5, so have from 1 to 2, 2 to 3, 3 to 4, 4 to 5. So we have to add all of them together to get from between 1 to 5, for example. That's why this difference here is really a sum of those individual ones. And each of them has an expression here. So it's a sum from I equal to m to k. So this will give you a decay process, a process of the forward rate on the k reset time. So finally, we have got a process that we can use to do simulation, for example, right? So I use simulation here as a way to visualize. So you can see sort of this fkt here for each k evolving into the future based on this random process. And as long as you know the volatility parameters that we specify here, and you know the initial value of f, then you basically are able to evolve here. Notice that there is a connection between the drift and the volatility as well, right? So the volatility actually parameter showed up here on the drift. Now, earlier we used this, and this is just a way to allow us to derive this. So why don't we use this to simulate? Because you are simulate a forward rate, and here if you use the volatility term of some process of zero coupon bond, that means you have to specify the zero coupon bond process, and you have to worry about the consistency between those two. So, but if you use this, as long as you specify the function for the volatility here, I can make it that parameter or a function of time, then that's all you need to simulate. Then by design, this process is consistent. So the consistency is guaranteed. And as soon as you simulate this process, and then for a future time point, you can then convert the simulated future future curve of forward rates, or the future simulated term structure of forward rates into a simulated term structure of interest rate, right? And just like what we have talked about for HJM. So then once you're able to simulate those forward rates and convert those simulated forward rates into the term structure of interest rate, then you can use them to calculate any derivatives on interest rate, any interest rate derivatives, basically, because they are just functions of the interest rate that you have simulated.